we're gonna talk about the optical applications of semiconductors like photodiode and light emitting diode. First of all, we're gonna look for the physical base of physical base of the optical device. So let's first look out for the relationship between wavelengths and energy. The wavelengths can be defined as in here, the ratio between speed of light and light frequency. So, and also the energy in quantum mechanics are defined as product between a Planck constant and frequency of light. So if we mix those two equations, we have here the relationship between wavelengths and energy. To make easy calculations, we pre-calculate the product between speed of light and Planck constant. So if we look here, we can know that through these equations that wavelengths are anti-proportional to the energy. So there are two mechanisms which are or opposite way. First of all, if the semiconductor gets light energy, then the electron hole pairs are generated, so that we call this light absorptions. We use it in solar cells and photo diode or sensors. On the opposite to this mechanism, there is if electrons are electrons on conduction band, if there is after the carrier's lifetime, then the electrons hole pairs would be recombined. During this recombine, the energies will be generate the same amount between the energy band gap. Also, when electron hole pairs are generated, to generate electron hole pairs, the energy needed from light would be amount of energy band gap. If the band gaps are direct band gap. For indirect band gap, there will be needed extra more power, delta K, so which is a thermal energy or something else. And there's another significant property, which is our photoelectric effect. The most important point on this effect is that the number of photons are not related to energy of light. The energy of light was related to the light wavelengths. So the intensity is proportional to the carrier's amount. So intensity follows to the Boltzmann distribution. So let's talk about the absorption mechanism. So in absorptions, when semiconductor absorbs the energy, the minimum amount of energy was the energy band gap. So we're gonna talk about conditions at junctions. So first of all, as light meets the junction between air or if if there's difference between reflective materials. So the Fresnel reflections can be defined as a constant R. R's are the light flux reflected over the intrinsic light flux. So which can be defined with those n named reflective index, which are reflect relative value to the air, like electron permeability. And there is a transmission coefficient. Transmission coefficient means that how much flux on the junction can be uh, absorbed, absorbed or passed through the junctions, not reflected. So after the light flux goes through these the junctions, then the absorptions will appear. Then how can we find that how fast how fast light flux decay? So like other uh, like diffusions, the light flux would decay exponentially. So we can define x0, which is point that light flux decay about to 37%. And let's talk about the alpha, the absorption coefficient. To make absorptions efficient, we have to the materials have we want to be material to be direct band gap, and also if the indirect band gap, the poor absorption efficiency would have, because when absorbing the energy uh, the amount needed to absorb was the energy band gap. In indirect band gap, they needed to the extra energy. So to make a good efficiency for the absorptions, the device should be thicker than the former X0, which is the light flux decay about 70, 37% of point. So the using this absorption mechanism, there is solar cell which are operated in reverse bias, and in depletion region, solar cells get energy, light energy, and generate electron hole pair on a depletion region. So after that, by diffusion, carriers move and generates the converts light energy to electrical energy. So there is solar cells would operate in negative bias or reverse bias region. So you can see that currents are same directions to reverse bias region. So if the equivalent circuit of solar cell is defined as here, the total current through the photo solar cell would be the saturation current no effect to the light and the current due to electron hole pair generation from uh, light energy. So if circuits are open like here, then the total current would not would be zero. So using this property, we can calculate the open circuit voltage through this. And there is two parameters of how efficiently solar cell can convert to uh, electrical energy. First of all, the quantum efficiency. The quantum efficiency means that how much current flux can be generated due to light flux, and the uh, repositivity is RPH, and that means that how much photon energy uh, dealt with uh, dealt with on solar cell can be generated to the current. It is important that quantum efficiency is uh, light flux to the current flux, so we normalize this charge. And there is a fill factor, which means that uh, how much uh, power on the circuits are converted to how much power of light can be converted to power at the circuit. In circuit, there will be operated with like MOSFETs or BJTs on here. Would be it will be have DC point, which means operation point would be here. Then the maximum power efficiency cannot over here. So fill factor cannot uh, bigger than the 1. For maximum conversion efficiency, we now know that the band gap should be direct, and we should know how which spectrum of light we want to observe, and the after electron hole pair generations, the current flowing mechanism is diffusion current. So to maximize the conversion efficiency, we have to make it longer to minority carrier lifetime, which means as minor carrier lifetime are proportional to the diffusion length, which in other way, if the diffusion lengths are long, then the carrier's lifetime will be also long. So in here, there is a definitions of this short circuit current, which means that the short circuit current with the conversion, the light energy to the electrical energy converted the ISC short channel current is related to diffusion length and the generation rate due to light flux. And there is a light emitting diode. The LED uses a right opposite mechanism to solar cells, which is operated on forward bias. And similar to the solar cell, the LEDs should keep those electron hole pair on the junction side. The more longer carriers exist in the junction, then the more recombinated carriers will be appear, which causes the higher light intensity. Now here the device structure is the heterostructure device. The reason we can say that is the energy band gap are differ in the junction. And there is another way to make the LED is that PIN, which means the combination between P-type and N-type between on intrinsic semiconductor. And there is OLED, which means organic LED. It uses a organic carbon base. Those are amorphous structures. And the reason why we use OLED is that it is very thin and it's very thin. So due to amorphous structures, the bands are not continuous. So we say that similar to the semiconductor, the concept of conduction band is LUMO and the valence band is HOMO. So